Let us look at this example. He's saying sketch root locus for the system given. So the system is shown there. If I want to draw it, first of all, I need to look at the number of poles and the number of zeros. Number of poles equal to 1, 2, 3, 4. So 4. Number of zeros are number of zeros equal to only 1. That means there are 3 elements will go to infinity. 3 elements will go to infinity. That means I need to draw 3 angles. At what location? At the location of sigma. So what is sigma equal to? It's the finite poles. Finite poles. What are the finite poles? They are -1, -2, and -4. We will put them here. Minus the summation of the final zero, finite zero. Finite zero is -3. So it's -3. Divided by the number of poles 4 minus the number of zeros 1. It's going to result on 4/3. That means at 4/3, 4/3 means 1.33. Let's say this is 1, this is 2. So at this location we will draw the angle. But what are the angles? You will calculate the angles in the next slide and you will find that one of them is 60, the other is -60, and the third will be 180. Let us see them in the next slide. So here is the angle. We need to calculate the angle 3 times. For k equal to 0, let's say k equal to 0, k equal to 1, k equal to 2. Why I am doing it like this? Because this is angle number 1, angle number 2, angle number 3. Why do I decide to make 3? Because there are 3 poles to infinity. So when k equal to 0, we substitute here 0. You will find that theta equal to pi/3 means 60 degrees. Of course, here, how to substitute? This is 2 into 0 plus 1 into pi. So 2 into 0 is 0, into 1, that means it's equal to pi over, what are the number of poles? 4, number of zeros 1, that means 4 minus 1 equal to 3. That's why it's pi/3. That's for k equal to 0. How about for k equal to 1? For k equal to 1, we will calculate it to be 2 into 1 is 2, plus 1 is 3. That means 3 pi/3. 3 pi/3 equal to pi. And same thing for the third one. So you will find the angle are 60, 180, and -60. -60 means 300. You'll calculate them as a 300. Okay. So we found earlier in the previous slide that the angles are to be drawn at the point of 1.33. So here is the angle. And here we will draw angle of 60, angle of -60, and angle of 180. That's it. But they are not root locus. These are a guidance to the root locus. They are not root locus yet. How to draw the root locus? Root locus is drawn here. This line, because we are having pole here, pole here, pole here, and pole here. So when you draw them, you will find there is line here, and line at this point, and line here. That's according to real axis segment. So between these two poles, between this pole and this pole, the poles are going to meet and they are going to flow toward infinity. Finally, they are going to meet with the 60-degree angle. They are going to meet with the 60-degree angle. This pole and this 0, they are meet with each other. Finish. The pole is going to the 0. Finish. And this pole will go with angle of 180 toward infinity. So 3 toward infinity. This one go to infinity, this one to infinity, and this one to infinity. Let us refine the root locus to find some elements which not discussed earlier, which will make us clear, or we can get the drawing more accurate. We can get the drawing more accurate with the refining of the root locus sketch. What we mean by this, you will see now. First of all, we are going to say real axis break-in and breakaway. What is a break-in and a breakaway? If you remember this graph, this root locus, which we discussed earlier, we said if there is a 0 here, it's not discussed earlier, similar discussed earlier, 0 here, pole here, and pole here. When I draw the root locus for it, we will find that here, real axis segment, and another real axis segment. So it's very clear that two poles and two zeros, that means they are going to meet on S-plane, nothing going to infinity. Means one pole will go to 1 0, the other pole will go to the other 0. That's to be kept in mind. Now, we find that the two poles which meet at certain point, so that they are going to leave toward the zeros. So it's going to meet at point here. They are going to meet here at this point. Then they will travel toward the other side. And we will come here. They will meet at this point. Keep in your mind that symmetry is supposed to be guaranteed, supposed to be given there. So they are going to meet at certain point, and then this go to the 0, go to the 0. So that's how the idea is going to be. Now, my point, or what he meant by break-in and a breakaway, a breakaway is the point where the elements or the poles are going to meet when they are moving. So it's moving this way, and this way they are going to meet at this point. So this point is what is known as a breakaway. And this point is the point called the break-in. Now, how to calculate them, the break-in and a breakaway, that's what will be seen in the next slide. So to calculate the break-in and breakaway, we are going to calculate K out of the closed loop transfer function. So K is equal to minus 1 over GSHS. And from there, we can express it in terms of sigma, because we will calculate for sigma. When you solve this element, you are going to come out with the arrangement for the equation. You will get the equation as a K into G of sigma into H of sigma equal to minus 1. It's just cross multiplication. Rearrange it again to get K. Let's go to the next slide. It's not shown clearly in this slide. This is example which will explain it. It's fine, no problem. But the K found earlier, we will differentiate it and we will find it equal to 0. From there, we will be able to calculate the value of sigma or S, however we call it, no problem. Let us apply whatever I discuss on this point. If we have the KGSHS equal to this value, that's what I have. What is this actually? Remember that it's the denominator of the closed loop transfer function. This is the denominator of the closed loop transfer function. Usually we have the closed loop transfer function equal to something over 1 minus K into GSHS. That's what we used to find. So if I take the denominator, we are going to find that this part equal to 1. Now, according to what I can say here, if you look at it, we find that GS is given, HS is given, and GS into HS will be equal to this part. Let us evaluate it, or let us put it in simpler form. We will solve it. We will put the equation in different way. So we will multiply this bracket into this bracket into this bracket, and we will find that it's equal to whatever you can see here. Now, as I mentioned earlier, K, G into H equal to minus 1. Now, if from there, I will make it as the K into G into S equal to minus 1 as given here. So from there, we can calculate K. So K will be equal to minus 1 over whatever you find from here. Now, once you put it, rearrange the equation and find dk by d sigma. Differentiate that function. When you differentiate it, you will get this value. This is the differentiation of the function given. Make it equal to 0. If you make it equal to 0 by cross multiplication, you will find 0 into this value is equal to 0, equal to whatever coming from here, which 11 sigma or S, no problem, sigma square or S square minus 26 sigma minus 61. This is sigma. This is sigma. Find sigma. Solve this quadratic equation. You will find two values for sigma. Again, I'm saying it's sigma or S. It's the value of S, but I'm calling it sigma just to say that this is the break-in and breakaway. When you calculate the value of S or the value of sigma, it's equal, we will find two values. One is minus 1.45 and the other is 3.82. So one of them will be break-in and the other is breakaway. That's it. One of them is break-in, the other is breakaway. So always, again, you will differentiate and you will make the derivative equal to 0 so that you can continue with the method I mentioned or the way I'm doing it. Another way to do the break-in and breakaway, he said you can do it as by finding the summation of 1 over sigma z means 1 over the poles S plus Z. As I told you, sigma is S. Sigma plus Z or S plus Z equal to the summation of S plus pole over or sigma plus pole. So when you do it, simplify the function and you will get finally the value of S. It's explained in the next slide. Here it is. So when we have Z equal to minus 3, we have this bracket S minus 3, S minus 5. And here the poles S plus 1, S plus 2. What he mean by the discussion earlier, the previous slide discussion, he said make it such that 1 over S plus S minus 3 plus 1 over S minus 5 is equal to 1 over S minus 1 plus 1 over S minus 2. Notice I am saying S or sigma because again I'm repeating, it's just the value of S because S plan accept S. But because it's break-in and breakaway, we will find that we give a specific or a special name for it, which is sigma. When you solve this equation, rearrange it, finally you will come out with this equation. Solve this equation for S, you will find that S has two values. It's a quadratic equation, second order quadratic equation. You will find two values for S. One of them is minus 1.45 and the other is 3.8, similar to the previous example. So one of them will be the break-in and the other will be the breakaway. In the refining of the root locus, also we need to know the j omega crossing of the root locus. What we mean by this point, if the root locus or as the root locus travel, it may cross j omega. So we need to know at what point it will cross j omega axis. What I mean by this again, if let us say we are having, this is j omega axis and the real axis. And let us say there is one pole, one pole, one pole. If I draw root locus, I will find that this line to be connected, this line to be connected. So according to behavior at infinity, this is going to go towards 0 at infinity. So it's going to take this direction. Let me change the color. And this one going to go with this direction and this direction. And they are going to meet at certain point. We call that point breakaway, if you remember. So we calculated. And then they are going to travel on angle of 60. Remember, 60 and minus 60. So they are going to travel this way. This is going to go this way toward infinity, and this is going to go the same thing. So if you notice, as the root locus travel, it will cross j omega at certain point. So when I say finding the j omega crossing, means finding the point where the root locus is going to cross j omega. How to do this? Luckily, we are going to depend on Routh-Hurwitz criterion to do it. We are going, whatever we have studied in stability using Routh-Hurwitz criterion, we will apply it here. Let us see how we apply it in the next slide. So if I have this kind of system and I need to calculate the j omega crossing for this function, we will find the closed loop transfer function. We have the characteristic equation. I hope you still remember. With the characteristic equation, we will build Routh-Hurwitz table. Here is Routh-Hurwitz table. We will find that the table, when it's ready, we have here this part. This part is important for us. Why this part is important? Because when I want to consider the value of k, remember we are looking for a point where j omega crossing. What is j omega crossing? When will I get this point? If you remember, we are going to reach this point when we have a row of zeros. If there are a row of zeros, we are going to get this point. And how am I going to get the row of zeros? When k is equal to certain value, that value will make this item all equal to 0. When this item all equal to 0, we are going to get what is known as a row of zeros. And once I get a row of zeros, we know we have something called even polynomial, or we can say we reach to the j omega. So what is the value of k which will take me to the j omega, will give me at j omega? To calculate it, we are going to make all this item equal to 0. From there, you are going to calculate to find that k will be equal to 9.65. When k equal to 9.65, this item equal to 0. That means for the value of k equal to 9.65, we will get a row of zeros. When the gain equal to 9.65, we will reach to this point. Remember, this point is not the gain. We said at this gain, we reach to this point. Again, at this point, we reach to this gain. But where is the j omega? Until now, I didn't get the j omega because the value, this is gain. This is not j omega crossing. J omega crossing is supposed to be a value for s. How to calculate the value of s? Let us see it in the next slide. Now to get the value of s where the response is cutting the j omega, we are going to get the value of k, which we found it earlier as 9.65. We will substitute it in a row before the row of zeros, and we will get the polynomial. So we are going to get this value. So here k, we will substitute 9.65 to it. That's what we are going to get, as you see here. Now, this equation, let us solve it. Take this one to the other side, then calculate for S2. You will find that S square, you will find that S square equal to minus 220.7 divided by 80.3. So S square equal to minus 202.7 divided by 80.35. So if you want to find S, of course, here you have minus. That means J will appear. Now divide this, find the, divide it first, then find the root square of it. You are going to find finally that the value of S is equal to plus minus J 1.59, which means if I want to show it on S plan, this is S plan here. We said as the pole changing or moving, they are going to move at certain point. Remember that there is line here, but I'm not showing it. They are going to split at breakaway, and they are going to cross j omega. As the gain is changing, they are going to go until they meet the j omega crossing at this point. What is the value of that point? It's equal to 1.59 j, of course, and here minus j 1.59. What was the value of the gain at that time? The gain at that time equal to 9.65. I hope now you are clear and you know the difference between the gain and the value of S at that gain, and you know how to generate the value of S at that gain. I think it's very clear now that the system, when you look at it, you look at the Routh-Hurwitz table, you will find that our system in the example mentioned earlier will be stable in a range between 0 to 9.56. If k get to be greater than 9.56, what's happening? The pole are going to cross the j omega to the other side. Other side means system is not stable.